I'm going to show you an example of the type of problem we'll look at in this chapter. I have this toy gun here, and it launches little foam darts. And the little foam darts are very, very lightweight, but they move very fast. And there's a quantity we're going to look at, and it's called momentum. Momentum is the product of the mass times the velocity of an object. And it's a useful quantity for treating certain kinds of problems. What kind of problems? Problems like this. If I take one of these darts and I fire it at the hanging globe, it gives the globe a little bit of a kick. And you can see it pushes the globe a little bit to the side. Now, the forces in that interaction are very complicated. But we can analyze the problem very, very simply if we use two terms, impulse and momentum. And those are the terms that are the subject of this chapter. And we're going to look at them in turn. We're going to start with impulse. I've got this giant soccer ball here. And this giant soccer ball, if I push on it, it deforms. And it comes back like a spring. It comes back like a spring. So if you kick the ball, it deforms. And how much the ball deforms is a measure of how hard you're pushing on the ball. Let's take it outside, give it a kick. We're outside now, and the soccer ball's sitting on the ground, but someone's coming toward it to give it a good, swift kick. Now when she kicks it, the ball deforms, and it deforms quite a bit, and that's because her foot is applying a rather significant force to the ball. Of course, the ball is pushing back on her foot, but we're interested in the force on the ball, and it's a large force. And you can see the amount that the ball is deformed starts out small, gets bigger, and then decreases again. If we were to draw a graph of the force as a function of time as she kicks the ball, it looks like this. It rises to a maximum and then drops back down to 0. Now that can be a very, very complicated force equation. It can be a very, very complicated force graph. But there's a term which will be of interest to us which is much simpler, and that's this. We're going to look at the area under that curve, the area under the force versus time curve. And as you'll see in the book, this is a quantity called the impulse. The area under that curve is the impulse. And it turns out the impulse is equal to something else. The ball started out at rest on the ground. After she kicked it, it was moving rather quickly to the side. So what changed about the ball was its velocity. But that means another thing changed, and that's the momentum. And as you'll see in the book, momentum is a product of mass times velocity. The initial momentum of the ball was 0. But later, the ball was moving very quickly, and so its momentum, the product of its mass times its velocity, was quite large. And it turns out, and this is the central piece of the chapter, the product of the mass times the change in velocity, and that's the change in momentum. The change in momentum is just equal to the impulse, which is the area under the force versus time curve. And this is something we've set aside, and we've highlighted this in the chapter because this is the central piece of chapter 9. The area under the force versus time curve, the impulse, is equal to the change in momentum. And this is a great way to analyze collision problems like the one that we've just seen. When you kick this soccer ball, it deforms quite a bit, and that's because it's pretty squishy. It doesn't take too much force to make this thing deform. A basketball is a lot less squishy. You have to push pretty hard on it. Suppose I kick this ball, and then I kick this ball. Well, this ball will make a much bigger force on your foot. You know this big squishy ball, the maximum force is going to be pretty small. But with this one, the maximum force will be quite a bit more. Maximum force, much, much bigger. Okay? Now these two balls have about the same mass. So I'm going to imagine the following situation. I kick ball 1 and I kick ball 2. They both fly off at exactly the same speed. They both have exactly the same mass. The change in momentum of the two balls is therefore exactly the same. The force versus time curve for kicking ball number 1 looks like this. What should the force versus time curve for ball number 2 look like? We'll give you some choices. Think about this. The maximum force when you kick this ball is quite a bit greater. But the change in momentum of the two balls is the same, so therefore the area under the force versus time curve has to be exactly the same. So we need to pick the solution that has a higher force, but it has the same area under the force versus time curve. And so this is the choice that you're looking for. The two key terms in this chapter are momentum and impulse, and we've seen a little bit about what they both mean. We can use them to solve problems, and the types of problems we're going to solve in this chapter are mostly collision problems. One object slams into another. But to be able to fully analyze a problem like that, we need to look at one more relationship